Okay, otherwise, radiation types. Right? You need a little bit of room here. I didn't probably leave enough on this slide in your notes, but just make sure you're not taking up a huge chunk of space when you do this. Right? There are three different types of radiation, and it's going to be alpha, beta, and gamma. Drawn about like I just did there. Right? There's supposed to be a little bit of a tail on the end of this beta, right? And I've drawn it from the bottom up. The alpha is a sideways fish. The gamma is actually a fish just pointing down. Right? These symbols represent three different types of radiation. And you're going to need to know the particles that go with those. The alpha particle is actually basically a helium atom. Right? It has for a mass, it's got 2 protons. Right? When you emit this particle, this is actually... we were talking earlier about how helium was discovered on the sun. So we knew what it was before we ever found it on Earth. We found helium by looking at decaying nuclides, right, that emitted this alpha particle. That's where we actually found helium for the first time. So it's a helium particle, helium-sized particle. It's relatively heavy compared to the other two. The beta particle is essentially an electron. Right? It's not an electron, but it has the same size in terms of it has no mass, and it actually has a negative charge. Right? So instead of a normal number there, you actually have a negative one for that atomic number, and that's going to affect things differently. You'll see that in a second. Essentially, emitting this negative particle, this very small negative particle, turns a neutron into a proton. Again, if the alpha is particle is heavy, this particle is very, very light, right? But then you have the gamma particle as well that really is just pure energy and doesn't have a mass and actually doesn't affect the atomic number at all either, right? It's 0, 0, and its mass relative to the other two is non-existent, right? It's so tiny that it'd be negligible. So we have these three different particles, and we just need to understand how that would work. So you're going to have situations like I'm going to do with examples on the right over here. So if I started out with a nuclide, right, a radium nuclide, so at number 88 on your periodic table, and you kind of need a periodic table to do this kind of stuff, but it may emit a particle to become more stable. If it emits an alpha particle, right, you have to remove that helium atom from that nuclide. And again, just like a couple slides before this, all you basically do is subtract that particle from the parent, right? So I have this 226 here as a mass. I'm going to subtract 4 from that to get 222, right? But I'm also going to do the same thing with my atomic number. By ejecting a helium atom, I lost 2 of my protons as well, so that's going to turn into an 86. And this is where that periodic table comes into play. You need to know what new daughter was formed in this context. So 86, I believe, is the atomic number for radon, and so that's your product. Right? You removed a particle in the process. A lot of times we actually write the particle on the right side as well. So I have this helium, excuse me, a little carried away there, this helium atom that's emitted in the process. If you take the 222 plus 4, you get 226. If you take the 86 plus 2, you get 88. So it should kind of make sense. It's simple, easy, whole number math. My next one, I'm going to have a radioactive nuclide for nitrogen. Right? This nitrogen 17 is unstable. It's going to emit a particle to become more stable, but it's going to emit a beta particle, right? And beta is a little bit different. The beta particle, again, has no mass, but it has a -1 for that atomic number. And what you're going to have to understand is that when I take 17 minus 0, it's still 17. But when I take 7 minus a -1, I actually add 1, and I end up with a new proton that didn't exist before. Again, we talked about how neutrons are slightly more massive than protons. Right? Apparently, if we emit this beta particle, that neutron can turn into a proton. So it has the same mass. I didn't gain nucleons, but somehow I have a new proton that I didn't have before. And again, now that I have that atomic number of 8, I actually have a brand new element. In this case, it's not a brand new element. It existed before now, but I have an oxygen atom as a daughter nuclide here. So again, you just emit a particle and you figure out what that daughter is going to look like. So same thing, right? A couple more practices. Let's say I have this 21483 bismuth atom nuclide, and it's going to emit an alpha particle. And then maybe I have a 24 sodium nuclide, and it's going to emit a beta particle. So you need to predict what daughter is going to be the result of this. If you want to pause right now just so you can check your answer, you should probably do that. But otherwise, it's fairly simple. If I subtract helium from this bismuth, I'm 210. I'm now an 81. If I subtract that electron particle from that sodium, I end up with still a 24, but now it's a 12. Again, you need to look at a periodic table. Number 81, I have to look across the room here. Turns out to be, I believe, a thallium, Tl. And number 12 is a magnesium. So those are my two daughters. Again, like I said, I should probably put a particle in there for each of these. That actually makes the math work out as a whole. But sometimes we do that, sometimes we don't. Kind of depends on what we're trying to do. So that should make sense for the most part. Otherwise, our last type of radiation is gamma. Again, gamma decays are a little bit different, so I have a special slide here, excuse me. So in this case, a lot of times you have an alpha and or a beta decay that also yields this gamma radiation. So it's usually not just the only thing that's being emitted at any given time, but there are some nuclides that only emit gamma particles, and if that's the case, you have to actually do a little bit of extra work in terms of labeling the parent and the daughter. So when it comes to an example here, these are actually the easiest ones to do, but if I write this out normally, I got a technetium 99, and it's going to emit a gamma particle, which again, the gamma has no mass. Doesn't affect the atomic number either. So my daughter is basically the exact same thing as the parent, which is where the problem comes into play. I don't really know how to differentiate between the two, right? So there is an extra label that we're going to put on the parent over here. We're going to put a little m next to that 99. It means that it's metastable, right? So it's not quite stable. It needs to emit that gamma particle to become stable. And so that's the only major issue with these gamma particles, right? But again, a lot of our previous examples, like maybe this nitrogen beta decay up here, right, could also emit a gamma particle, and it wouldn't really change much because I'd still end up with an oxygen 17. I just have an extra little particle over here that didn't really affect the math one way or the other. So it doesn't matter if it's an alpha, a beta, either one of those can be accompanied by gamma radiation, but that radiation itself doesn't really affect the math, so it doesn't really change much. So as long as we understand that, I needed that metastable label here for my parent because I needed to be able to indicate that this parent was not stable, that it could become more stable by emitting a particle, whereas the second technetium lost that label. It now is stable. It's not going to undergo any more decays. Whereas again, back here, I could throw in that gamma. I didn't need a metastable label because the daughter and parent are obviously different to begin with because a nitrogen is different than an oxygen. So I don't really have to worry about that. Okay, that should be good enough for now.